Very good morning to all. So we are discussing the different signal generators. So in this session, in the previous class, we have seen the basic standard signal generator, which generates the sine wave, and standard signal generator, and also laboratory signal generator, the function of the signal generator, and also let's see the generation of sine square waveforms in the audio frequency range. Shaper. So the generated sine wave will be shaped by square wave, and after that it will be amplified by amplifier circuit, and it is attenuated, and you will get square wave output. So with this we can generate the sine and square wave outputs in the range of audio frequency range. Function generator. So it will make the function generator will generate so all the four output forms. So generally we can generate the sine wave, square wave, triangular wave, and sawtooth waveform. So with this function generator, we can generate four types of waveforms: sine wave, square wave, triangular, and sawtooth waveforms. And we can adjust the frequency. So we can adjust the frequency for this function generator. So there is a frequency control option will be there. So with this frequency control option, we can change the required frequency, desired frequency. Okay, and we can reduce the frequency. We can reduce the signals in the frequency range from fraction of the hertz to the hundreds of kilohertz. So we can produce 0.01 hertz to 100 kilohertz. So in this particular range, 0.01 hertz to 100 kilohertz, in this frequency range, the function generator will produce three types of output waveforms. So by using this function generator, we can adjust the frequency range. Okay. So here the main feature of this function generator is, so we can get all the three in this function generator. We have three outputs. So here square wave we have, triangular wave, and another one is the sinusoidal wave. So in some generators we can available only at a time, only we will get single output, but in function generator, so we can get all the three outputs at the same time, all the three output signals at the same time. So that is the main feature of this function generator. Suppose we want to test the linearity of a circuit diagram or amplifier. Suppose we want to test linearity of an amplifier. So for that we will apply the square wave input, and we can observe that output of the waveform in the CRO. We can observe the output of that transistor output in the CRO. For that, we have to require the sweep signal, a sawtooth waveform signal. So that sawtooth waveform signal also can be generated by the function generator. So it will produce 3 output waveforms we can use wherever it is required. So that is one main feature of this function generator. And another one is phase locked capability. So if one function generator will lock the another function generator, I mean the signals which are generated in the one function generator can be locked by the other function generator, and we can produce the same phase at the output. So we can adjust the two signals for the same phase. Suppose one function generator generates the sine wave signal, and another function generator produces the sinusoidal signal, but having certain phase variations. So with this function generator, we can lock the another function generator, second function generator, and we can observe both the signals. We can observe both the signals by varying the phase. By changing the phase also, we can observe how the two output waveforms will be generating, or output waveforms are producing, amplitude and frequency. Okay. So generally, the function generator, in general, in audio frequency, sine wave and square wave generators, we used Wien bridge oscillator. So in that Wien bridge oscillator, we use the LC network or RC network. We can call it as a tank circuit. So by adjusting the value of the capacitor, we can change the frequency of the generated signal. So generally the frequency variation is done by adjusting the capacitance value in a given tank circuit, whether it is RC circuit or it is LC circuit. We have two types of tank circuits. By these tank circuits, we will get the oscillations, and those oscillations, the frequency of generated oscillations can be changed by changing the capacitance value. So in the previous audio frequency sine and square wave generator, we used the Wien bridge oscillator. So in that we can change the frequency by using the capacitor, changing the capacitance value. Okay, so that is one type of the changing the oscillations. So for the function generator, we don't use the such type of oscillators. Tank circuits we are not use. So in this function generator, we will use a constant current source. Constant current sources. We will use two constant current sources. One is upper constant current source, and second one is lower constant current source. And these two are connected to an integrator circuit. The integrator circuit. So whenever the upper constant current source is connected to integrator, the capacitance will be, the output of the integrator will be linearly increases. It means the capacitor will be charges. When the capacitor will be charges, we have a positive slope at the output of the integrator. So at the output of the integrator, we have an output voltage. So that is nothing but the due to the upper current source. So when the current source is connected to integrator, we will get an output voltage. That output voltage is increased. So that is The capacitor, in this case, the capacitor is charging. So capacitor charging means, so the slope of the uh, uh, capacitor value, I mean slope of the output voltage is increasing. So increased slope, this is increased slope. Okay, in such situation, the voltage comparator multivibrator, here voltage comparator multivibrator. So whenever the capacitor was charged to a predetermined maximum value, the this multivibrator will produce a pulse. By that, the upper constant current source is disconnected and lower constant current source will be connected. So there is a switching mechanism will be available here. So by that switching mechanism, whenever the positive slope or the output voltage of the integrator will reach a predetermined maximum value, the voltage comparator or comparator multivibrator will produce a pulse signal, will produce the output signal. So that output signal will be makes that disconnection of the upper constant current source, and it connects the lower constant current source to the integrator. So in the when the lower constant current source is connected to integrator, so it will produces the reverse current. It produces the reverse current. So by the connection of the reverse current to the integrator, so whatever may be the voltage will be the charged potential across the capacitance will be discharges, and that's why the current will be in the reverse direction. Here in this case, the current will be in the reverse direction. Whenever uh, whenever due to voltage compared multivibrator will produce a pulse which disconnects the upper constant current source and connects the lower constant current source, and this constant current source is in the negative current source. That's why the capacitance discharges and the current direction is in the reverse to the upper current source. So in such situation, the output voltage will be decreases. That is nothing but discharging of the capacitance. So discharging of the capacitor, whenever the output voltage is reached to a predetermined minimum value, whenever the output voltage reaches to a predetermined minimum value, so that limits values are set in this voltage compared multivibrator. So in the voltage compared multivibrator, there is a predetermined maximum value and predetermined minimum values will be arranged. So according to those values, whenever the output voltage reaches to a predetermined minimum value, again this multivibrator will be produces an output signal. So that output signal will be produces the changes the uh, this switching position. In such situation, the lower constant current will be disconnected and upper constant current source will be connected to integrator. So again, the current will be from the upper current source will be positive, and that positive current will be flows through the capacitor, and due to that, the integrator output is a linearly increasing slope, and that output voltage is increases to a particular level. The output voltage reaches to a predetermined maximum value, and again the output voltage produces a change in output voltage, so that will be makes disconnection of the upper constant current source and connection of the lower constant current source. With this, again the lower constant current will generates the negative current. So in such situation, the capacitance will be discharges, and due to that the the output voltage is decreasing. The output voltage is decreasing. So whenever the output voltage decreases to a predetermined minimum value, again the multivibrator will produce a pulse, changes the pulse, and those pulse will be connected to the upper circuit. So like this, the cycle will be repeats, and like that we will get the Like that we'll get the triangular waveform. Like that we'll get the triangular waveform. So triangular waveform. Okay. So here whenever so we will multivibrator will produce a output waveform. So to change the current sources. So to produce that pulse. So that is nothing but the square pulse. So when the predetermined maximum value is reached, up to that it is producing positive. After that reaches that, so it will produce as the negative pulse. Negative pulse. It will be up to in the negative value only. After the output voltage reaches to the predetermined minimum value, again the comparator will produce the higher pulse, high output pulse. That high output pulse will be again makes the connection of the upper current source. And after reaching the positive value, again it will produce as the a pulse. Again we will get the lower value. So like this, so when we connect the voltage comparator output, so that is nothing but the square wave. That output is nothing but the square wave. If you consider or if you take the output of the integrator, that directly gives the triangular waveform. That directly gives the triangular waveform. If we connect the triangular waveform output to a resistance diode shaping circuit, if we connect a triangular output to a resistance diode shaping circuit, so with this we will get the square wave output. With this we will get the sinusoidal output. We will get the sinusoidal output waveform. So here this is triangular wave slope will be changes. See here up to this triangular waveform and sinusoidal waveform slope is same. So by applying the resistance diode network, the slope of the signal will be changes at peak value. After that, again it is producing a linearly decreasing value. Like this, there is a sinusoidal signal shaping circuit is usually from the triangular waveform. So like this, we can produce the three types of output waveforms by using function generator. So I think you understand the basic operation of the function generator. So if you have any doubt or clarification, you can raise, or you can write in chart. If you understand, okay. Okay, shall I go to next slide? So here the output voltage. So output voltage is following this equation. Output voltage is equal to minus of 1 by c equal of 0 to t I dt. So based upon this equation, the capacitance charging and discharging that will be represented in the output waveform, which is a integrator. Integrator output voltage is 1 by c equal of I dt. And coming to next one is a square and pulse generator. So the next type of the generator is square and pulse generator. So the difference between square wave and pulse outputs is nothing but the only the difference is duty cycle. So duty cycle, you know that. So duty cycle is nothing but the pulse width by pulse period. Pulse width by pulse period. A square wave generator is having a 50% duty cycle. So a square wave is having a 50% duty cycle. So it means the falling and rising timings are same. The rising time and the falling time of this square wave is same, that is 50%. And to get the different pulse waveforms with different duty cycles, also we can use this pulse generator. Pulse generator. So if you change the duty cycle of the duty cycle, so we can get the square wave. So if the duty cycle is 50%, then we can say it is a square wave pulse. So that can be also produced by using this pulse generator. Pulse generator. So generally with this, we can produce a frequency range of 1 Hz to 10 megahertz. So with this pulse generator circuit, we can, this is the pulse generator, block diagram of pulse generator. So with this pulse generator, we can produce a frequency range of 1 Hz to 10 megahertz. From 1 Hz to 10 megahertz range, we can produce this pulse generator. Okay. So here we have, here also same, we have a switching circuit. Switching circuit is there, and upper current source and lower current source is there. So in place of integrator, we have a schemic trigger. So schemic trigger will produce the hysteresis output. I think you know the operation of the schemic trigger. Schemic trigger produces the hysteresis output. Okay. So here the switching circuit is connected to the schemic trigger, and upper current source is connected to schemic trigger, and the output is, so this is the basic operation of the pulse generator. You see, so the in the like in previous function generator. So here we have two current sources, constant current source I1 and a constant current source I2. These two constant current sources are connected to the schemic trigger, and that current source is connects to a ramp capacitor. Here this capacitance is nothing but the ramp capacitor. So here whenever the current source is connected to this schemic trigger, the current will charges this capacitor, and whenever the capacitor will be charged and the voltage across the capacitor is reached to a predetermined value, the schemic trigger will changes